Okay. Hello everyone, I'm Viktorija and we'll be presenting LeviCursor today. This work was done under the supervision of Professor Jörg Müller at the University of Bayreuth. Okay, so what is LeviCursor? LeviCursor is a method for dexterous interaction with the levitating cursor. And the cursor can move in all three directions smoothly, and it can be directly controlled by the user. LeviCursor, as you might imagine, can be implemented, can be used for 3D selection of physical objects where all natural depth cues are important. For the motivation of our work, we go way back to the 60s to one well-known vision in HCI of Ivan Sutherland, who envisioned the ultimate display as a room where the computer can completely control the physical matter. So, for example, we can make a chair appear and disintegrate, so it will be a truly a merge of the real and the virtual. And this vision has been very persistent through the years, and here we list some of the advantages of the ultimate display as opposed to, for example, augmented reality glasses. First of all, the content that is displayed is real, so we can see it, touch it, and the user does not need any device to interact with the physical content of the display. Everybody who is in the room sees the same thing, so it encourages discussion and collaboration. And 3D depth cues, contrast, focus, illumination are all correct as we know them. And also the physical matter is tangible, and as we know, people get adapted really early on to be able to process physical information. So one of the implementation, or one of the attempts at the ultimate display is with the method of active atoms. So this is the work on programmable matter from 2005 from Goldstein and colleagues, where the physical content is created by using miniature atoms, which can assemble and disassemble on a 2D surface. Now the challenge with using the active atom approach is the cost per unit, the power supply, and the miniaturization. So that's why we moved to a passive atom approach, and here it's in the form of acoustic levitation. So in our case, we use a display composed of two opposing arrays of transducers, which emit ultrasonic waves at a frequency of 40 kilohertz, and within the nodes of these ultrasonic waves, we can trap small particles. These small particles are the passive atoms, and all the intelligence, the power supply, and the actuation comes from the environment. So, of course, if we want to implement this vision, we want all of the particles to move smoothly at a high velocity, and we want them to be stable. But since this is a big task, we start first with one particle, so that's our LeviCursor, which can be used for selection in 3D space. Now for the HCI perspective, of course, interaction with such display is very important. So we look at some related work. So for example, pixie dust. Pixie dust was a setup of 4 transducer arrays, which by using the method of standing waves create a 2D grid of levitation traps. And the user can interact with the system using a Kinect, and that looks like this. And the next example is of LeviPath, where we have two opposing arrays with a smaller display area, and the user can interact with the lip motion sensor. So as we see, there have been some implementations of interaction with levitating matter. However, in order to create a cursor which will have the performance that the user expects, there we have identified some areas of improvement. For example, the system needs to have low latency. So of course, if a user is moving the cursor, the user wants to perceive it as a real-time interaction, so the latency needs to be very low. There shouldn't be any jumpy particle movement or jitters, and the cursor should move at high speeds and accelerations. Okay, so now a bit of the technical side of our implementation. So when we have a levitating trap, the spherical particle experiences acoustic force from each direction, and we model this using an equation from a physics paper by Gorkov, using the Gorkov potential, which is a function of the acoustic pressure and the spatial derivatives. And why this is important? For the basis of our implementation, we use a BFGS optimizer, which was presented 2015 by Marzo and colleagues, where we use the algorithm to generate a trap. So to generate a trap at a specific point in the acoustic field, we optimize the parameters for the transducers in such a way that at this point we have maximum acoustic force and minimal pressure in order to have a greater stability of the particle. As a summary of our contributions, with LeviCursor we achieve a system with low latency, high frame rate, and smooth interactive control of a levitating cursor. Then we develop a mechanism such that the levitating particle always stays in the main levitation trap. There are also secondary levitation traps. We will go back to this. And to validate our findings, we conduct the first 3D Fitzlaw type pointing study with a levitating cursor and physical targets. And now I hand on to my colleague Myroslav.
Hello, so I will tell about the actual problems and how we solve them. So first, concerning the continuous movement of the particle, in order to achieve as smooth and continuous movement as possible, we need to be able to place particles at arbitrary positions. And optimization algorithm is able to do that. However, optimization takes a lot of time to be in real time. The most real-time implementation could look like the one here, when the particle would jump only after 2 seconds. So our solution to this problem was, instead of running BFGS optimizer in real time and trying to respond as fast as possible, we select our levitation volume, we discretize it in a 3D grid, and then for each grid point, we compute phase values using BFGS optimizer, and we store these values into a lookup table. Then we can use lookup table in real time to specify transducer value, phase values to the transducers, and control the levitation trap in real time. So while discretization, we can do it as small steps. In our case, it was 0.5 millimeter steps. It still is not continuous. So in discretization grid, the particle would move between different points of the grid. And we wanted to achieve smooth movement. So we wanted to be able to move the particle in between the vertices of the grid. In order to achieve that, we apply 3 linear interpolation scheme. So basically, we take 8 neighboring vertices and compute interpolated value based on them. As a prerequisite for this interpolation, we need to ensure that the phases are smooth within that small region. So to evaluate the smoothness, we have evaluated it for the whole levitation volume, and we have identified that in 95% of levitation volume, the phases are smooth, as you can see on the left plot. However, there is still 5% of the volume, and in particular closer to the transducer arrays, in which the phases have abrupt jumps. And interpolation in such regions with abrupt jumps would result in inconsistent phases and drop in the particle. So in our algorithm, we identify these abrupt jumps before interpolation, and if we have this abrupt jump in the local position, then instead of interpolation, we fall back to the phases contained in the nearest vertice. So the next challenge was placing particle into the main trap. To place the particle, we would usually turn on the ultrasound field, use acoustically transparent material to put the particle in the field, and remove their material support. But there are problems, because we cannot actually see where is the primary trap and where are the secondary traps. As you can see, there is one primary trap in which the particle is enclosed with the forces from all sides, and there are secondary traps which can support particle against gravity, but when we try to move it, the particle would drop because of lack of forces from different directions. Also, such secondary traps can disappear during the movement. And this would again lead to dropping of the particle. So our solution to this is using optical motion capture. So first, we create ultrasound field using transducers. Then we put the particle into the levitation volume. The particle is observed by motion capture system, so we know where it actually levitates. And at this point, we don't care whether it is primary trap or secondary trap. We can use the place identified by motion capture system to specify where the primary trap should be. And control system would identify the necessary phases for primary trap to match the position of the particle, and reset the primary trap to the position of the particle. So we do this particle stabilization in the initial phase when we place the particle into the field. However, often when we move the particle too fast, it can jump from main trap into the secondary trap. So in order to avoid these jumps, we would still regularly reset the main trap to the current position of the particle using the same method. So our system hardware consisted of two opposed transducer arrays with 252 transducers in total. Both arrays were connected to a single ultra haptics controller board. Using single board was necessary in order to achieve synchronization of both arrays, because even if the sound would be unsynchronized in fraction of milliseconds, it would lead to uncontrollable behavior. So the other part of the system was a motion capture system from OptiTrack with 6 cameras. 3 of them were tracking the particle, and the other 3 were tracking the fingertip. So both parts of the system were connected to two workstations, and between them they were connected by a local network. So the workstations were optimized, first one for real-time response, because levitation hardware required our system to respond within 1 millisecond, and other workstation was optimized for processing throughput. To evaluate the system, we performed 2 types of evaluation. First evaluation was evaluation of stability at different speeds. So we have moved our particle multiple times at different velocities, and we have computed frequency of particle dropping at different velocities. So we have identified that at 0.8 meters per second, we can have 100% stability, and it drops to 0 at 1.2 meters per second. And up to this point, this is the highest velocity reached by a levitated particle. Then we evaluated latency of the system using a high frame rate camera. The camera was observing levitation volume. We have generated an optical event and recorded the response of the system in terms of dropping the particle. And then we computed the number of frames between these 2 events to identify the latency. And on average, the latency was 15 milliseconds with maximum latency 17 milliseconds, which are actually both below 20 milliseconds, which need to be, for the system to be considered real time. Then we have performed fit-slow pointing study, just to evaluate how the system is performing in interactive tasks. So the targets were represented as spheres centered at the tips of the needles. And then the participants need to move between these 2 needles. And as soon as the levitated cursor reaches the target, the participant would hear auditory feedback. What we found out that the pointing with levitated cursor behaves similarly to pointing with a mouse, and it follows fit-slow model. And fit-slow model has goodness of fit of 0.92, and the users achieved with the system effective throughput of 4.9 bits per second, which is comparable to mouse and is only slightly below uninstrumented pointing with the hand. So as future work, we consider a few directions. One of them is trying other algorithms for real-time phase generation for the transducers. Other direction is control of multiple levitating particles. For example, if we have 3D object represented out of them, then third direction is using LeviCursor as a selection technique to select among other statically levitating particles. For example, if we have some particles represented 3D visualization and we want to select parts of visualization. To conclude, we have implemented a 3D pointing system with levitating particle, which allows interactive and agile control of the particle. We have evaluated the system in 2 technical evaluations and in interactive fit-slow study. And we have solved our challenges of low latency, smooth continuous movement, and keeping particle in the main trap using precomputation of transducer phases, interpolation scheme, and particle stabilization mechanism. So, thank you.
Yes, hello, Michael Kipp from Augsburg University of Applied Sciences. Amazing work. Thank you very much for the talk. I was wondering about the Fitts-Law task, which is really hasn't been done in 3D in a proper way. How do you signify the targets, and how does the user show that he or she has hit the target? How do you clutch in a way?
So the targets, it was a bit hard to represent them in 3D. So we used needles. So let's see the video here.
What about the diameter or width of the target?
Diameter or width were not really visible, but the user know the targets are the spheres centered around the needle tips, and we had spheres of 3 sizes, of 2, 4, and 8 millimeters. And the user would hear auditory feedback as soon as the LeviCursor reaches the target.
Okay, got it. Okay. So, but did you use depth, or is it basically a 2D or even 1D task?
So the cursor can be controlled in 3D.
Yeah.
So before the actual pointing task, the users would try to move the cursor and control it in 3D.
But are the needles on
actual
the plane?
pointing task can be considered as 1D because it is.
So they are on a plane and on a single line, basically.
So
the needles.
The movement of cursor is 3D.
But the task is 1D, basically.
The task is 1D.
Okay. Thank you very much. Yeah.
We have spherical targets.
Hi, Stacy Scott, University of Guelph. I have a follow-up question on the Fitts law test. Was it always this, like a side-to-side motion? Did you do any front-to-back? I'm just wondering in terms of the understanding of the mapping of the input space to the motion space. Is there any difference in how users are perceiving like a side-to-side, how accurate, and depth perception?
As I already told, users were able to move the cursor in all 3 dimensions. So they were also able to move it in depth and in height. But we observed that they moved basically between targets in 1 dimension mostly.
But for the specific user test you did, the Fitts law test, was it just side-to-side, or did you do any front-to-back target motion?
This was only small Fitts law study. So we had only these 2 targets.
It was just that,
in
okay.
this study.
Okay.
So we haven't performed studies with this type of pointing or vertical pointing.
Okay, thank you.
One last question.
Yep.
Thanks for the very impressive work. So how was this control display gain was set when you conducted the experiment?
It was set 1:3 control to display ratio. The movement of human fingertip was observed by motion capture system, and sometimes it might be a bit shaky. So that's why we set it 1:3. So basically, a bit larger movement of the hand was mapped to smaller movement of the particle.
Okay, thank you very much. Let's thank the speakers and congratulate them for their honorable mention award.